Probability is kind of the study of how you can start from a model, some probability model of and then make statements about outcomes or observations that might be generated from that model. So taking our example from earlier, our model was the number of times you flipped a fair coin, and then using that model, we were able to say, okay, the probability that x equals 2 after samples from the model is equal to 2%. So statistical inference is really the process of going in the other direction. You start by observing something in the real world. So still drawing the analogy with the first example we saw, you could imagine that instead I didn't tell you that the coin was fair. What I told you was that I flipped the coin 3 times, and maybe I did like n repetitions of that, and then the n values of x were a given set of data that I'm giving to you. And then suppose I ask you, given that that's the case, what's your best guess for the probability that the coin lands on heads after I flip it once? That would be the process of starting from a sample and then trying to recover the model that was used to generate those samples. And maximum likelihood estimation, which I abbreviate MLE in this document, is a method that helps you do this process called statistical inference, going from observations in the world and trying to reconstruct the probability model or the statistical model that was used to generate that set of observations. So I hope that was a bit easier to parse. Let me know if you have any questions. I'm gonna kind of transition to a concrete example that really illustrates this a bit more concretely. So imagine this fictional scenario where you own a store. Let's say your store only sells one item, so like one type of item, and you want to estimate the number of people that arrive on any given day. But it's not enough for you to just know the average number of people arriving at your store. You also want to know the probability that you might get a lot of people arriving, or the probability that no one arrives at your store. And you can assume that each person who arrives at your store definitively buys 1 unit of the product you're selling in this example. Yeah, so can anyone think of why that might be useful to be able to think of the probability that you get a certain number of people arriving to your store?
To see how much stuff you sell and then to see how much revenue you make.
Yeah, exactly. Yeah, that's exactly why it's important. It's also really important too because what if what you're selling is perishable? You might have to throw out any extra units you have at the end of the day, and then at the beginning of each day you might have to order a set of units to keep at your store, in anticipation of people arriving. So having this information would also, in addition to allowing you to estimate how much revenue you'll generate, it'll also help you know how much product you need to keep, in the store available to customers as they arrive. So that's what you're trying to do, and that's why you're trying to do it. And what you're given access to is that over the course of n days, you count how many people visited the store on each day. So these variables, little x1, x2, ... xn, represent the number of people that arrived at your store. So those would be, non-negative integers. So 0, 2, 3, 5, etc. So this is what you observe, and you're trying to figure out how you can now start from that and reconstruct your probability model. So here I'm going to introduce something called the Poisson distribution, which is an example of, another example of a distribution. As Ms. Ayag mentioned earlier, there are tons of probability distributions. This one in particular is one that's generally accepted to be a good way to represent arrivals. So arrivals of people, or also it can be used to represent the number of times a rare event occurs in a given time interval. So the way to understand this formula is that x is the random you're observing. So the probability that x equals some fixed value k. Think of k as sorry, okay, I forgot to write it down, but k is a non-negative integer as well. So the probability that your random process is equal to um, any fixed non-negative integer is equal to this expression. And I can comment on this a bit more later if anyone's interested, but this distribution actually results from taking a nicely defined limit of the binomial distribution that we introduced earlier. So that's a really nice connection, and that's where it comes from. Someone didn't just like pull this out of thin air. They got this by taking the limit of the binomial distribution. So this distribution is parameterized by this value lambda, which is a continuous, a real valued parameter greater than 0. So it can be 2.5, it can be a decimal number or a fractional number, it can be an irrational number if you'd like. So in our distribution from earlier, when we were talking about the coin flips, the kind of two parameters were the number of times you flip and the probability of the coin being heads when flipped once, which was 0.5 in our case because we were working with a fair coin. So here we only have one parameter, and it's this lambda parameter. Okay. So now the problem is now we've said this is a reasonable way to model the arrivals at the store, but we're left with figuring out what the best choice of this parameter lambda is, starting from the data that we observed over those n days. So what do we do? Well, we can do what's called maximum likelihood estimation. So I'm going to define this likelihood function here, for L of theta, and you have the sequence of data you observed here. So this is a function. This is a univariate function in theta. Theta is the variable, and you can interpret these little xi's to be fixed constants for the purposes of the likelihood function. And this function represents the probability of observing this set of data if theta is the parameter of the Poisson distribution, right? So if theta is equal, if lambda is equal to theta, then L of theta gives the probability of observing this set of arrivals over n days. So we can actually write out directly the functional form of L of theta. Does anyone have any guesses or ideas on how you might do that? So think that on each day you're observing xi arrivals. And on a single day, the probability of seeing xi arrivals is equal to this expression where you replace lambda by theta. So now we're talking about observing these n arrivals on n different days. So how might you combine those probabilities over n different days to get the joint probability of the entire process? So kind of similarly to what we did earlier, you multiply the probability of the individual events happening. So this, I don't know if you've seen this symbol before, but this means multiplication from I equals 1 to n. So this is you're multiplying, probability that capital X equals x1 times probability that capital X equals x2, etc., all the way until xn. And this is actually the extension of what we did earlier when we multiplied the probability of seeing several instances of a coin flip back to back. Here again, we're multiplying the probability of counting this number of arrivals. And when I substitute in this functional form we introduced earlier for the probability, this is the form I get, where again, think of the xi's as being fixed and theta is your variable. So this represents the likelihood of observing this set of outcomes when theta is your parameter. And what we're going to do is we're going to estimate the value lambda of our probability distribution by choosing the value theta that maximizes this likelihood function. And we're going to maximize it over the interval 0 to positive infinity because we know that our parameter lambda has to lie in that interval. So that's the only interval we care about. Okay, so hopefully this is somewhat in a form that is a bit familiar to you. You have some function of a single variable theta, and you want to maximize it over an interval. How would you do that?
Do you have to do like a derivative test?
Yeah, awesome. That's exactly what we're going to do. We're going to do a derivative test, and we're going to see what we find. But first, notice that, so what you'd be wanting to take the derivative of this function with respect to theta, but notice that we have this product over n terms here, which is really, nasty to work with. You don't want to have to do product rule like n times. That sounds like very labor intensive. So what we can actually do is we can take a modified version of this function. Instead of maximizing this function directly, we can maximize the log of the function. And the reason it makes sense to maximize the log of the function is because log is a strict, and when I say log, I mean the natural log. So log is a strictly increasing function. So if you know that, some value maximizes a function, well, that same value will also maximize the log of that function because log is strictly increasing. So you can preserve that ordering of the values. And now when we take the log of the likelihood function little l is now called the log likelihood, all of the products turn into sums. So now this is a lot, you can imagine this is a lot, nicer to work with because instead of, having to do product rule, now you're just taking like derivatives of terms that are additive. So it's a lot simpler to do. So you can look through how you get directly from like capital L of theta to little l of theta, on your own time if you're curious. Does anyone, so starting from this function then, little l of theta, can anyone tell me what the derivative of this with respect to theta is? So theta is your independent variable. That's what you're taking the derivative with respect to. And then everything else is just a constant.
Was it like 1? So you have like 0 and 1 for theta?
So kind of like try to work through this piecemeal, right? So just looking at this term, so this sum of the xi's is a constant. So you can, like, that's a constant that'll just get pulled out. So what is the derivative of log theta? Or so this is the natural log, okay? So like think of it as theta. I imagine you've seen it more on ln. So like what would be the derivative of ln of theta?
1 over theta?
Yeah, awesome. And then what would be the derivative of n times theta?
N?
N. And then what would be the derivative of this last term with respect to theta?
Well, log?
Sorry?
Well, like the derivative of log xi?
So yeah, so the derivative of this last term, but with respect to theta. Think of theta as being the variable.
Is it is it like a 0? Like there's no theta?
Yeah, 0, exactly. There is no theta, so this is just a constant. So the derivative with respect to the constant is 0. So when we take the derivative, this is exactly what we get. 1 over theta times the sum of the xi's minus n. That's your derivative. And when you set the derivative to 0, you get that the derivative is equal to 0 when theta star is equal to the average of the values you observe. So theta star is your critical point. It's the only one you found doing the derivative test. What would be the next thing you were to do if you had to decide whether or not this is a local max or local min?
You have to check like values before and after for if it's increasing and decreasing?
Yeah, you could do that. Yeah, so you could definitely, try plugging in values kind of like, nearby the data star and seeing what the value of the thing was. But there's also a way to do this, by looking at the second derivative. So you could imagine taking, is this something that you've done in AP Calc, kind of using the second derivative to check whether something is a max or min? Yeah, awesome. So you can do the same thing here. You can take the second derivative of L of theta, little L of theta. So here, you know, the 1 over theta becomes a minus 1 over theta squared. You still have the constant, and your minus n goes to 0 or goes away. And this is negative for all values of theta, which means that the function is concave down. So theta star is a local max. Yeah, so that lets us conclude that theta star is a local max. And you can actually kind of verify that theta star is actually the global max because, so I mean, yeah, I guess we don't need to say too much about this, but you can check that the boundary limits of this function go to negative infinity. So theta star is truly like the global maximum of the function. So what's kind of the upshot? It means that after observing this set of arrivals on n consecutive days, your best guess of the distribution of arrivals on subsequent days is given by this Poisson distribution, where the parameter theta star, which is what we were calling lambda earlier, is given by this average of what you've seen previously. So now you're able to make some statements about the probability that you see, you know, 5 people showing up next day, or the probability that you see 10 people showing up. And yeah, again, it's also not a coincidence here that the parameter is equal to the average of the arrivals. And yeah, I can definitely comment on that if people are curious. But yeah, that was just to give you a taste of maximum likelihood estimation. It's a really core concept in statistics. People care about this in, you know, economics, in medicine, in finance, in chemistry, at literally any field where you would be estimating a value from a data set. So definitely a very important topic.
So literally, Nick, you could choose any industry that you're interested in, like race cars or travel, and somebody would hire you to be their mathematician to help them make decisions. Wow, it's very versatile. Yay, math.
Can you actually choose race cars though?
Can you actually choose race cars?
Yeah.
Yeah, some of the major motor companies have some of the most elaborate data science and like statistics teams. Like Ford or like Ferrari, they have a lot of statisticians working for them.
Damn.
So officially, class is over. So I need to respect the fact that the guys might have somewhere to go. So we have time, if you're okay to stick around for a few minutes, if guys want to stick around, just to ask some follow-up questions. But I definitely wanted to thank you and wish you good luck with your PhD at MIT. Is that the next plan?
That's the next step, yes.
Beautiful.
Jesus.
And don't forget, if you're in town, come by for lunch, eh? It's still free for you.
Thank you so much. Thank you so much. I'll definitely take you up on that.